we got, I believe that's called doubly ionized narrowband filter for oxygen. And what this does, and I've seen this out in the uh, out at Big Woods when the camera is hogging my telescope, and I go and look through everybody else's. So I deeply appreciate that because it gives me some new appreciation of doing things visually. Not to mention it's cheaper. So here we go. O3, or excuse me, oxygen, doubly oxygen narrowband filter. So I think it was Jim that showed me this a while back. Either Jim or someone else. They had this filter, and I was looking through their scope, and it was a Newtonian telescope, and probably a Dob most likely. And we looked at the Ring Nebula in '57. So Ring Nebula, this is best used on planetary nebulae and supernova remnants. And looked at the Ring Nebulae, and the nebula looked exactly the same with the filter on. The only difference is that everything else was super dark. Okay. Now, because the light is blocked out, or excuse me, because the filter is blocking out everything but oxygen, that means everything else should have been deflected by the filter. So, by that rationale, and I've seen this also visually, it does work to an extent under light pollution. So, if you have a bright enough DSO object like the Ring Nebula, I can't really think of any others. But anyway, under light pollution, it does contrast a lot better. It's almost as if you were in a little bit darker place. Use one of these filters under light pollution. So, okay. So the next one does some really weird stuff, and I brought one of these with me, and it's a polarizing filter, and it helps to darken all of the electromagnetic spectrum. Okay, so everybody's probably heard of neutral density filters. Okay, so if you were to just take one of these, they come in pairs, but if you were to take one of these, it acts just like a neutral density filter. So, but as you move it back and forth with another polarized lens, it starts to deflect more light. So let's see, where is it? No, I need it dark in here. Ah, there it is. Okay, hold on one second. All right, so here are two polarizing filters or a pair that I have, which will vary the light based on the way it's deflecting the light. If they crisscross, you'll see less light. So everybody can see this pretty well, right? Okay, so if I twist it, you'll notice that it goes dark and then gets bright, goes dark and then gets bright. This is really useful for objects that are really bright, like say Mars or Jupiter, but it definitely, saves the day as far as your dark adapted image if you use it on the moon, even though it won't be too dark adapted with the moonlight out. So anyway, that's polarized filters. And another application for this is because the way it diverts light is you have this stuff, this type of filter built into sunglasses. So if you're looking at a car directly in front of you and you have your sunglasses on, they have polarized filters on it, or the lenses are polarized rather. Lift your glasses up and the glare is much stronger. Okay, so when you put your glasses down, not only because the glass itself is darkened, but what happens is the light just gets boosted into almost right angles. At least that's what the diagrams I looked at show. So there you have it for sunglasses. Does anybody else know what polarized filters can be used for? I'll give you a hint. You can use another example is they're built into a special type of pair of glasses. Anybody know? 3D, right. Okay, so the latest movies in 3D use this concept the way that polarized lenses are able to redirect light. So if you film something from two different aspects, you have one camera here shining or recording the movie on the right side, and the other camera over here recording on the left side. As it brings in that light, the polarized filter in your 3D glasses brings the images together, and bam, you have your 3D movie right there. And in fact, I believe polarized lenses were actually the first what the first 3D glasses were made of, and I'm a big movie aficionado. And if I can remember correctly, it's either the Creature from the Black Lagoon or It Came from Outer Space is where 3D cinema got its start. So, do what? No, they weren't. No, seriously, they weren't. They were polarized, yeah. But red and blue, yeah, red and blue is what you would use. You could do that to practically any movie if you wanted to. It's just that you're off-centering the different color channels, and you'll see something sort of like that when we get onto imaging filters. So let's see. I'm sorry, do what? How does that work?
See it.
Okay, very good. Yeah, could you explain that again, actually? Yeah, there you go.
Okay, can you hear me better now?
Yes, we can.
If you have two polarizers, one a big one, or if you can use the sky, which is partially polarized on blue sky, 90 degrees from the sun, and you want to check out a piece by rotating it. This is dark at 90 degrees from the sun, or get darker. But that's one polarizer. You cross it, and if you have stress in the glass or a piece of plastic, usually injection molded clear plastic, styrene, has a lot more stresses than glass will. Although I've got one 8-inch blank that has a spectacular bullseye with cross lines in it in color. That is totally useless. But I don't know whether it has any annealing or whether it would blow up if you started grinding it. But it isn't Pyrex.
Okay.
So you can check out glass on that. If you have a problem with the refractor, you can check your lenses just to see if they're stressed. Sometimes you might not have something that's...
so you can use these things basically just to check the quality of what you have, right?
Yeah, check the quality of your glass, and they do some structural analysis on some complicated things by machining something out of plexiglass and putting the whole mounting holes, and make a duplicate piece of what they're going to have in some aircraft parts, and they can see how the stress concentrations run.
Very good.
So that's another use for polarizing filters.
Very good.
If you can also use it for shooting fish.
Shooting fish. Oh, wait a minute. Yeah, I know what you're talking about. Yeah, because it gets rid of the glare that's on the water surface. Yeah. Okay. Very good. Also helps with sunlight when you're trying to get a good look at clouds.
As a reminder to folks, we are streaming this on Google through YouTube, so that's why we have the microphones. The microphones aren't connected to the PA system, rather connected to the system.
Okay, so
we're having these little technical difficulties.
Okay, very good. That's fine, yeah. Okay, now we move on to something I'm a little bit more knowledgeable about since, yeah, I just got schooled on polarized filters. Okay, so not only can cameras pick up visible light, they can also image in the near infrared and UV. Some can all go, of course, all the way into infrared. And so moving from visual filters to imaging filters, because imaging cameras can also see different light other than the visible spectrum that we see with our own eyeballs. This is another aspect that we can use filters to exploit the light coming in. So imaging with filters can also demonstrate the nature of how light behaves in our atmosphere, as is the case visually. Reflectors are best because the only way that you can get the best raw photons coming into your eye or into a camera sensor is with mirror surfaces. All right, keep doing that. Okay, so first we'll do red, green, and blue filters. Okay, so this is just a color scheme that I don't know who came up with it exactly, but RGB, red, green, blue, is an electronically additive color model, and what it's based on is that if you have red, green, and blue, and depending on how you add the different intensities of each color, will determine the overall tone of the image that's hitting the sensor. So, in this case, what do you call it? Red and blue, learned in kindergarten, make purple. In this case, we call it magenta, whereas green and blue, so blue-green, makes an almost turquoise color, or cyan. And it's kind of hard for me to explain exactly how red and green work to make yellow, but the best way I can describe it is that if you have a pale red, I'm going to say it's film, or even a pale red filter and a pale green filter, you'll see that it makes more of a yellow color than it does a brown color. So that's the best example of how I can give how that works. So UV and IR are blocked from the camera sensor because obviously these are used for the visual spectrum. Okay, so imaging filters. Because we're just looking at individual areas of the electromagnetic spectrum, at least with RGB, we're talking about the visible spectrum, light that we can actually see. But now, since we're not looking at it, we're just casting it on an imaging chip or sensor in our camera, we get to see what is actually red, what is actually green, and what is actually blue here. Okay. So here, don't pay attention to the IR. I'll get to that later. But if you remember, let's see. If you remember, red being all the way here on the left, what's next to red? Well, infrared. So I'll get to why I did infrared later for Mars. So these are RGB or IRGB filtered images of Mars. They are all of the same time frame, roughly. I did IR first. Green and then blue, so it may have rotated just a little bit, but for our purposes, let's just say that we did it all simultaneously. So first off, one thing that you can go ahead and extrapolate by looking at all these filtered images. If you look at IR, you can see the polar cap. Now, it's not as bright as it is in green and blue, but you can actually see it, okay? It's a lighter gray than most of the land formations around there, so it's lighter. You get into green, it gets a lot brighter, and then when you get into blue, it gets more intense. So before we even see how these images are combined and make a full-color image, what does that tell you about the light coming from, or that's getting reflected off of the ice? What color would it be? No? If you can see it, well, if you can sort of see it in infrared, and you can see it in green, and you can see it in blue, what color would the ice caps be? White. Right. Very good. So anyway, the other thing you may notice is that infrared, or even red for that matter, filters out most of the stuff that's in the atmosphere, and obviously anything green and blue. So you get a look at what the surface of Mars is, which is actually red, right? Because it's called a red planet. So that's why you see the most intense regions of white versus the green and the blue. Now, as you go down in green, since you're filtering out the red planet or the redness of the red planet, you start to see other features more clearly. and in this case you can see the ice cap really, really well, and then also you can see the cloud formation starting to pop up there. And remember, if you go back to the last or a few slides ago, I was talking about the green filter being really good for Mars, the green visual filter rather, being really good for Mars. Here, it just further validates that, because you see all features here. You see the land formations, you see the clouds, you can see the ice cap really clearly. Green is great on Mars. Okay, so again, you see how the other pattern you see is that you see the surface of Mars in red. Then you come up from the surface, you start to see clouds, you see the ice cap. Then you come further away from the surface, you don't see the land formations as much anymore, but you start to see a lot of the what the additive nature is if we combine them all together, make a red, green, blue image. So, let's see. Oops, keep doing that. Okay, so going back to that diagram of how RGB works and creates all the different color combinations, this pretty much fits it to a T right here. You got your red on top, you got your blue to the left, and you got your green to the right. So what I did in Photoshop is, this is an image I took like the middle of last month of Mars, and what I did is I just took the individual mono images and just made them their raw color. So that's what the infrared one looked like for red, the blue one for blue, and the green one for green. And so you put them all together, you can already see the different shades of magenta showing up, cyan and yellow, put them all together, and there is your RGB image of Mars. It shows you the upper clouds that you saw in blue, all the way down to the red soil that was shown in infrared. We can also show it in the red filter. So anyway, one set of imaging filters. Next darn it. Next we move on to how does my images compare with the way NASA does use RGB filtering, and well, obviously NASA wins. One thing I like about this is right here, you can see that in the topography, you can see the shield volcanoes from the Tharsis Bulge area. There's Olympus up there, so what I'm assuming, this was actually, I go back, this also shows something else very interesting. So you see this face of Mars over here in the full color image. You can see the land formation in that image has moved over in this image. So you can go back and forth. You can see how the planet is actually different from the previous image to this image. And what I did here, and I intentionally did here to demonstrate that this was taken to show you, as far as just science goes, well, it shows you some weather going on there. Because right around in this area, here, that is what the cloud detail looked like 3 days before this right here. So, and also what's really nice that I pointed out earlier, you got the Tharsis shield volcano as well. If they're really high peaks, obviously the clouds will have to slither around them, and that's exactly what happened right here. And so I'm guessing that this spot right there may be Olympus Mons peeking through. So it tells you a lot of stuff. It doesn't really accentuate the depth of Valles Marineris, but you know, I like what this image can tell you, and especially when you compare it to 3 days before. Anyway, RGB filtering. Okay, next we move on to UV and IR filters. Now these two filters I have myself, and one of them is a UV filter, and the other one is the infrared filter, which I'll show you here. Let's see. Okay, so I'll show you the infrared filter that I used on that Mars image there. And let's see. So I don't know if you can see it that well, but I'm just going to move it back and forth. Do you see how it's kind of reflective there? Okay, because this is an imaging filter, your camera, once again, doesn't just only look at visible light. It also looks at infrared. It can also look at UV. And what you're seeing there, that coating is supposed to get rid of infrared, or excuse me, get rid of UV, because this is an infrared filter. Not supposed to get rid of infrared. Okay, so anyway. If you look at the picture up here, you'll see it says 742. That's what this is. It's a 742 nanometer transmitting filter. So that's what it's supposed to let in. That's in the infrared region. Have UV. This one, I've only been able to use it successfully twice. And one thing that's nice about our atmosphere is that when we go outside, even if it's dark outside, we're not getting fried by UV. Okay? We have clouds, we have water vapor, we have just the raw atmosphere in our way. It's bouncing UV out into space or off to the side, but some UV still gets through. If it didn't, we would never get sunburned or even tan, right? So I have that filter right here, and it goes really deep into the UV to the point I don't even know if you're going to see the flashlight through this. So can you see it? No. Yeah. So you need a very big aperture to use this, and I've been using it on my C9 1/4. But going back to what I was saying, how UV gets bounced off everything that it could possibly go through. What do you think you have to have as far as sky conditions go to be able to image in UV? You have to have some of the best seeing conditions ever. Okay, that way you get all that UV going through, and you'll be able to get an image. Going back to the 3 telescope designs, once again, the best thing to use to bounce UV rather than to bounce UV towards your camera sensor, or God forbid your eye, are mirrors. Okay, whereas if you use something like a refractor, it's going to bounce UV off, and in this case, since we have 3 elements here for this triple apo refractor, it's going to filter out UV that much more. So that's the other problem I have as far as using this filter, is because I use it through a C9 1/4, which is just like this guy right here. It's just a tad bigger. And, well, it's got that glass plate in front. Then it hits a mirror and a mirror, so that's not bad. But then it goes through a Barlow, which has 2 elements. Then it goes through the filter, which itself is not going to be super duper perfect. Okay, so in the end, you hope that you got a really good image. And I've only gotten one satisfactory image out of this so far, but I haven't given up on it. And as time goes by, maybe I'll have something to post and show the club as far as how it works.
Quick question: would you gain anything using the IR Pass 850? It's a
8 IR. I don't know what that is. Oh, you mean?
Yeah.
You mean the
right
higher?
The
higher?
Yeah, it's above
Yeah.
the
Well,
742.
Yeah. So, well, the further away you go from UV, and so thank you for saying that. Actually, the further away you go from UV, since UV gets bounced around in the atmosphere, infrared actually can penetrate better through the atmosphere because of the longer wavelengths of its nature. It gets through the atmosphere a lot better. But the one I have that you see on the screen right here, that filters around the 742 nanometer region, which is more near IR, not necessarily all out IR. So if you get a filter that has a longer wavelength than that, like this one was made by, I believe it's Astronomic, made this one. It's called the Planet IR Pro 742. They have a step up from that. It's called the 807. And kind of like UV, it gets darker because, well, that's just the way you're filtering the light out. You're getting so close to IR, you're no longer seeing visible light anymore. But it does increase the contrast with regards to seeing. So you get a nice crisper image if you use IR. Hence the reason, because IR is right next to red, that's why I used IR here. Okay, so if I would have used IR 807, probably that top image, which is supposed to be the red channel, I used IR for it. But if I had used the other filter to astronomical cells, I have the 742 nanometer. The one that goes further down I'm talking about is 807. 850? Oh, okay. All right. So, yeah, I'm wrong. All right. 850. The planet would look a lot stiller, depending on, actually, it would be stiller in regards to the same seeing conditions that this one was taken. So, which is kind of good. I may actually go ahead and just get one of those filters, and the reason why is that the last two Mars oppositions for the one we just had now wasn't that great as far as size-wise. It only got up to somewhere between 13 to 14 arc seconds. This one was a tad better. It got somewhere between 15 to 16 arc seconds. But unfortunately for the northern hemisphere, and probably most of you know what I'm about to get at here, is that the next oppositions will be further into the ecliptic, the summer part of the ecliptic at night. And if everybody knows where the ecliptic is at night, because the northern hemisphere has summer, the plane of the solar system is down further on the horizon, whereas during the day, because we have summer, the plane of the solar system is way above us. Well, if you have a planet there in the middle of the night, especially here in North Carolina where we have super humid conditions, you're going to be staring through a lot of seeing there. So if you can get an infrared filter that's longer than wavelength than that 742, that will help just a little. We'll see what happens. So yeah, 2016, I believe it gets up to 18 arc seconds, and then finally, 2018 is about where Mars was during the famous opposition of 2003. Not as close, but pretty much in the same position in the sky. And the opposition of 2003, just like the one in 2018 that we're going to have, was really low in the sky. So I'm holding out for 2020 for the best images. And 37 now, I'll be 43 then. So a lot of hurry up and waiting in astronomy here. So, anyway. Okay. Okay, so let's talk about UV filters again. And like I said before, it's very sensitive to seeing. And as I said before, also because UV gets bounced around a lot, thank God our atmosphere actually does that, as we would be all burnt to a crisp right now, right? Okay, and so my most successful images of looking at Venus in UV, because UV will enable you to see cloud structures on Venus. I showed you that one UV filter here, and you shined the flashlight through it. Nobody could really see the light going through that filter, so that means you need a pretty big telescope to transmit that. Not only that, because it's UV, you're going to need some pretty good seeing conditions as well. So what you can do is you can actually use the RAC 47 visual filter, because it goes down to that area of the spectrum, close to UV, or relatively speaking. Okay, so by that rationale, it should pretty much do the same thing, and that's exactly what I got here at the top. Not super impressive, but you do see cloud detail here. However, once again, seeing rules the roost when you're trying to image in UV through a UV filter. And so you have the top one that was under good seeing conditions. Here's a bottom one that's in UV, believe it or not. And, well, we didn't see any cloud structure, needless to say. So anyway, and also for all your imagers out there, so you're thinking to yourself, well, the RAC 47 filter is used for, it was designed for visual use. The thing that you do have to take into consideration is that if you're using a camera that's sensitive to close to the UV side of the spectrum, it's most likely also sensitive to the IR side of the spectrum. So once again, there's another piece of glass that you have to put in the way of that filtering of when you're filtering for UV. So that much more glass in front of it, and that extra piece of glass is an IR filter. Because using the RAC 47 gets rid of everything from like red all the way up to violet, but infrared can still get through, which your camera can see. So you need to block that off as well. So anyway, so that's what Chris was able to get. So it's me versus NASA again, and I lose once again. So this is what we have. This is like probably my best UV image I got, and this is one of the Mariner missions. Does anybody know which Mariner mission this was? I just grabbed this off the web. Does anybody know? No? Okay. Well, anyway, it's a false color image. Okay, so Venus, everybody knows, they've seen it through a telescope. They know it's not blue. All right. So, but I really like this picture, so I thought I would just give my image a slight blue cast there, kind of in homage to that image there by Mariner. So anyway. Okay. Darn it. Okay, moving on to IR. Okay, so as we went over before, IR is able to get around seeing quite a bit, and because of that, if you use it with a camera sensor that's sensitive to IR, you can filter out everything using an IR filter, filtering out everything but IR. And these are images I used with IR filter that I shined the light through earlier, my 742 nanometers. And as Michael Mantini said, the further you go into the towards the infrared end of the visible spectrum, the better off you are with taming seeing conditions. So anyway, bad seeing, no problem. And you look at the way this is working with IR, what's beyond IR? Does anybody know in the electromagnetic spectrum? Starts with AM. Microwaves. What's after that? Radio waves. Okay, and we'll get to that later. So infrared can penetrate through our atmosphere and tame the seeing. Just imagine if we can get something that uses long wavelengths, just like infrared, and put it out into space and look at something using radar, which uses radio waves. So once again, this is my image. I cannot do that. So which craft did that? I can't remember. Does anybody remember? Magellan. Okay. All right. Very good. So anyway, here's Venus, and because they were able to penetrate, well, they didn't have to worry about our seeing. They actually were able to penetrate the seeing, quote, seeing on Venus. They were able to get a pretty good map out of the surface, which had been obscured up until then. So just like we implied right there, obviously, the longer your wavelengths, the more you can see through objects. You know, just like when infrared hits an object, it heats up, or right here, when we're talking about radio astronomy, wavelengths so long, you can, quote, observe through the clouds. So that's the benefit of imaging at longer wavelengths. So, darn it. Okay, so here we have something that Hubble did with infrared. Penetrated through gases and dust and was able to see the trapezium a lot better, including the star field surrounding it. That. And I believe the next big heavyweight as far as taxpayer dollars of using infrared is the James Webb. Is that correct? Yeah, very good. Okay, I remember something. Okay, so, all right, next set of filters that we'll use. So, if you remember, well, first let's go over this. So these are narrowband filters, and they target very specific wavelengths of visible light, okay? Ones that are given off by hydrogen alpha, doubly oxygen, sulfur. And what you can use is you can use these just like red, green, and blue and assign them their individual channels, and then they can tell you exactly what the composition of what you're looking at is based on the ionization of the gas that's in the object you're observing, or in this case, imaging. So, but because it's such a specific wavelength, if you're going to use a camera, well, it's the only thing you can use, but when you use a camera with this, just realize that if you're imaging like red, green, and blue, you're looking at a chunk of the red, chunk of the green, on the blue, a chunk of the blue. So you got all those collection of photons in each of those sections. Whereas here, you only got, well, very few areas where photons can get through. And in this case, it's where sulfur, oxygen, hydrogen alpha can get through. So, and those are just really tight areas of the electromagnetic spectrum. So anyway, but again, because it does this for hydrogen, oxygen, and sulfur, it can give you a good look at what the composition of the object you're looking at is composed of. Anyway, composition. Anyway, so the most famous arrangement of this is to assign sulfur as your red channel, green for oxygen, and blue for, actually, no, I got that in reverse. No, these are scrambled. Okay, sulfur red, hydrogen green, oxygen blue. Boy, that's I did that. Jeez. Okay, so anyway, but since it, one of the nice benefits of this, you have to collect a lot of light, so that's the downside of it. But if everything goes to plan, collect all of those images, you're able to get good enough long exposures to get enough sub-exposures to stack. Because the wavelengths are so specific, it won't take in moon glow. It won't take in light pollution. You can do this in Central Park if you wanted to, okay? The only exception, this is something I read from, I can't remember his name. He's a big narrowband aficionado, but he said that the narrower your oxygen filter is, the better, because oxygen, narrowband filter for oxygen does lead to light pollution. So, these are astronomic filters. These are probably the ones I would want. Here, astronomic is pretty economical with all their filters.
If you had gone that route, Venus shots, how much more deep? You got any more contrast?
Okay, well, again, this is, I mean, that's a good question right there. I'd be just curious to see what would happen, but again, this is all dependent on hydrogen, oxygen, and sulfur. Okay, so, I mean, just off the top of my head, I mean, well, we got sulfuric acid rain, so we know that sulfur is there. Sulfuric acid has oxygen in there. Well, just about everything has hydrogen. I don't really know what would happen if we did. That's interesting. Give that a shot sometime, maybe. Okay, so right here, I got this off the web. It was from, do what?
Another question, not kind of a comment on your narrowband filters for visual use. One of the things that really impressed me was an O3 filter view of the Veiled Nebula in Cygnus. It reduces the brightness of the stars, which, if you look at it just with visual light, with no filter, it's there. It looks pretty good, but it just brought it right out and suppressed the stars. The stars got a broad spectrum, even though they have the oxygen light. They're very suppressed, and both from photography and visual, it's spectacular.
Okay.
I remember the view that I got on a very clear night with the 24 an O3 filter. That's permanently burned in.
So, well, here, because you've seen, you've had more experience with the O3 visual filter. You know, I said that right there. It works to an extent under light pollution. Place it help with that? Maybe? Does anybody know that?
The visual ones are about 50 nanometers,
Okay.
and yours is what, 5 angstrom narrowband imaging, so that's half a nanometer.
Okay.
So you're letting in a lot of continuum light from the moon,
Okay.
and it's pretty bad. That's why your O3 has a problem, right? It's wider because it's getting the doublet of O3.
Okay. All right. That makes
filter.
sense. So going back to what I was saying, that pretty much means that, you know, the narrower my oxygen, the better. The oxygen narrowband filter. Okay. I thought it was mostly light pollution is what I read, but for the moon, I guess there you go. So. Anyway, so here's an example. I don't have any narrowband images myself, so I got this off the web, but just looking at the selection of images that he had uploaded onto the gallery. Did you know him, Mike? Yeah, yeah. seems like he was a really fast learner just based on the few images that I saw him.
If you go into the hobby too fast, you get bored with it pretty quickly because there's only so much you can usually image. So I think he moved on to other things because you have to go to dark sites even with narrowband to do most of the interesting objects.
Okay.
Because you're going to talk about, we're talking about, if you look at these images, probably 20 hours of integration at least.
Yeah.
Right. Most RGB things people do with Canon is like 3 or less. So it's pretty time intensive.
Yeah. But that does go back to the fact that you're just collecting a very small select group of photons, right? Yeah. All right.
Chris, I'd be really curious. I don't know if Steve can do it on this. Do the fast star approach. Get it down to 2.
Yeah. Well, obviously you can cut back on your subs, right? Yeah. Yeah. But again, so the whole point of this, so I've read on the web, and actually I'm happy that I was able to figure out this question that somebody asked. They asked that, going back to Astronomic, if I were to get narrowband filters, I probably would go with Astronomic because they're cheap relative to, like, say, Astrodon or the other manufacturers. But they have 2 hydrogen alpha filters available. They have one that's 12. And I believe that 12, what's the term I'm looking for? Nanometers, thank you. Angstroms, thank you. Yeah, angstroms. They have one that's 12 angstroms, and then they have another one that's even narrower, meaning that it's picking up a even smaller stream of photons. That's half that. I believe it's 6 angstroms. So based on that, somebody asked, it's like, maybe I should just get the 12 angstrom filter because it can collect more light. And I was like, yeah, well, it can collect more light, but it doesn't mean that it's collecting hydrogen alpha faster, okay? Okay.
The speeds in these clouds is tens of kilometers a second.
Yeah.
Figure out the Doppler shift of that. It's going to be very small. So that you're not, it's much wider than the natural width of the hydrogen line.
Okay.
Even at 3 angstroms.
Not angstroms? Okay. Okay.
So yeah, you what you're doing is that reduces the stars more.
Okay.
Now,
So
you asked about the fast star. The thing you have to worry about at F2, a lot of these filters will not work very well. Because I had an epsilon TAC at f2.8, and that was getting on the edge of what some of these filters were expected for.
yeah.
So you could have a problem.
So what does that mean as far as, like, in regards to aperture versus
Yeah, I think
whatever?
the light cone is coming in so steep.
Oh, okay,
the
light
way these
cone.
filters
All right.
work that you start to have problems.
Okay, I see what you mean.
Versus, at f10 on a cast screen,
Nice,
it's not
nice and square, pretty much. Okay.
When you tilt them, if you look at a narrow band filter or even a visual semi-narrow band filter, if you tilt it, it will vary the color considerably.
Yeah, yeah, I've seen that before. Yeah, I know what you're talking about. Anyway. Okay, so anyway,
Sorry,
you have
Chris,
here.
Can I ask one more question?
Yeah, sure.
Folks, what object is this? This Eskimo?
No, this is Rosette Nebula.
Rosette. Okay, thank you.
I would say this is probably like 2 degrees, maybe. So 2-degree field of view. Anyway, I can't remember. I want to say it's 2244 NGC. I can't remember. Anyway, okay. So you take the sulfur, assign it as red, take the hydrogen alpha, assign it as green, and then oxygen as blue. And just like the old one that we looked at back a while ago, the Mars image using RGB, do it now with narrowband. Okay, so there you go. So same thing, same concept. You just merge each filtered image that you have, and kabam, there you go. You have a nice, pretty picture. And when I look at that, it's pretty. Who cares what it's made of? So anyway, all right. Pretty much at the end here. So no. People probably don't know the name of it, but can somebody describe it? Maybe you know.
I'm going to say the pillars of creation.
Very good. I don't have a cookie to give you, but anyway, yeah, there you go. So
That's part of the Eagle Nebula M17?
M16.
16.
Yeah. Does everybody know what it means by pillars of creation? No? Okay, very good. Won't have to go into that much. And any questions? Once again, if you want to ask me questions about visual filters, I'll do the best I can. But there are a lot of people in here who have more experience with that than I do.
So, Chris, I've got a question, and I'm sorry we're dealing with some technical difficulties. Did you mention the ultra high contrast or the UHC filters at all for visual use?
You mean as in like or like it's almost like a neutral density filter, but it's for everything except astronomical light. Is that what you mean?
Yeah, I don't know the exact specs, but I mean, I know for visual that seems to be something that really works. I know it does have a pass through in the O3 as well as I think two different hydrogen levels.
Okay.
I don't know if anyone else can comment on using UHCs. It seems to be kind of a more generic filter.
They said it would help with the, just for visual.
Mm.
I don't know. I don't see it.
Yeah, I have a UHC filter, and I've used it several times. It's great as a general light pollution filter and a nebula filter. So you've got, I believe it's got band pass at O3, O2, and H alpha. So it's pretty versatile. So you're getting a varied light filtering through that. I kind of experimented with that a few years ago with looking at using my Bader solar with the UAC filter, and it's kind of the sun looks kind of funky with that, but it's pretty interesting because there's a little more detail, a little more granularity on the sun than you get with just the white light filter off the Bader. The other thing too I find is that when you use a Bader solar filter, a lot of times there's some flaring off that filter, and so the UHC helps reduce that flaring. So it's kind of interesting. Sometimes I play around with mixing and matching my neutral density, and I also have a double ring polarizing filter with other filters, and I find that also helps to knock down some of the glare and stuff that you get off the planets and stuff.
Kind of on that note, they make imaging filters that sort of do the same thing. I bought one just for giggles one time. This is the Orion Sky Glow. See what it does. This one's the cheapest one I could find, and I'll just say that it works to a small extent. So if you want to do imaging under Sky Glow, you can use this, and but then again, you'll probably only be able to push your histogram over on your camera just a little bit further, not very much at all. But if you did do it, for one thing I did notice, kind of makes sense, but if you were to go over and start having that Sky Glow leak through even this guy, what I noticed is that if I did it under sodium vapor lighting, it wasn't that orangish color. It was just white. That's what the gradients I would see from sodium vapor lighting. You use this filter. Anyway.
The wheels and filter sizes and actual cameras that you're using.
Yeah, okay, so both visually and for imaging as well, you get some the general sizes you'll run across are just ones that will thread into your eyepiece, your filter wheel, or onto your camera. So 1 1/4 is the standard smaller eyepiece, and then you have your 2 your larger wide field type eyepieces. Now, the thread is universal across almost all accessories in the hobby. So another thread that's out there that's not as commonly used, they have filters that are almost this size, almost 2 inches, and they're made to be thread on the visual back of an SCT as well. those aren't as common, and to me, I don't really see a benefit in doing that so much. But you know, just put it on whatever you're looking at, whether it be your eyepiece, diagonal, whatever. So, but filter wheels do the same thing. They have the threads for putting your filter that you would use to put filters on your eyepieces. The filter wheels have those same threads, so you can screw them on there. I'm sorry, to what? Oh, versus the actual the mounting that it's in.
Standard filters
Okay.
or standard filter wheels, and people like the 30 magenta and the salmon color 85 from Mars, and those are available through Scope. People were actually punching glass out of other filters, swapping them out, used them that because they couldn't get the filter if they could have.
Was it too big or too small?
Well, they were too tall. That's why I'm asking the question.
Oh, too tall in diameter? Is that what you're saying?
No, too tall vertically, so that you put an adapter ring to put them in there, then the filter.
Oh, okay. I think I see what you're saying. Okay, very good.
I don't know. I've not seen too many, and I don't know how much variation there is between filter wheels, but I know the people over at Southeastern Camera would like to see a filter wheel. She's adapted, the person that makes those adapted some filters, but she's not sure if they'll actually
clear the inside of these things.
So if anybody's over at Southeastern Camera and
Where's
has
yours?
a filter wheel, take it over.
Where's your filter wheel? That ginormous one. How thick is that one? That's about the same thickness as this. Yeah, I would think so too. Hmm. Anyway, you didn't really get to see this um, in the dark, so I'm just going to show this right quick. So this is the filter wheel. Everybody was asking questions about filter wheels. This one's set to IR. This is actually just a UV and an IR blocking filter, so nothing comes through but visible light in the camera. You can use this for a color camera with a Bayer matrix in, which automatically blends red, green, and blue. I'm not going to get into how it does that, but those cameras can also be sensitive to UV and IR. So that one is IR right there. Oops, won't have an accident. Okay, this one is green right here. Okay, you can't really tell, but it's because it has that coating in it that also blocks UV and IR. And so here you go. Okay, the next. That one should. And I use, like I said, IR tames seeing a little bit, so I use that mostly in place of my red, but I do have red on here. And good. I like this. It's that UV and IR coatings. Red channel side. Now, as far as imaging goes, really, as far as like using your different filters, the best telltale sign whether or not it's going to be a good night is if, again, the further you go over towards the UV end, which in our case, red, green, blue, the blue would be closest to UV. If you look at your blue filter, that's going to show you if you look at the live image of what's coming through your blue filter, that's what's going to determine how good your night's going to be because it's most effective by seeing. So if it looks pretty good, then the night's worth it, I guess. So.
I've had to change focus, certainly, especially
Yeah, yeah, and I have to do that here too, because IR isn't. When people sell their filter sets, their RGB sets, they just assume that people are just going to use the red, green, and blue that they gave them. Okay, a lot of people know that you would use IR for red, but because they don't do that as an IR green and blue, it's yeah, of course it's not going to be parfocal with your green or blue, but it's just nature of the beast, or nature of the strongman. Lots of trade-offs. Anyway. Thanks.
Thank you, Chris.